integer. So we can say an integer is a whole number. That is, it does not have a decimal or remainder. So let's just save that as a thought on our whiteboard. And by the way, we're using slightly different software to see if this is a little bit better in terms of switching back and forth and providing the content. And so if you know that an integer, you know that they exist on the number line. The number line is presented here. We know that anything that is to the right of 0 is positive, anything to the left of 0 is negative, and we know 0 is a transition. Now this number line is presented with integers. We know that there are other numbers in here, decimals, but we're specifically in this part just talking about straight integers. And so we learned when we looked at the number line that if you look at positive 4, the opposite of positive 4 is minus 4. And we learned also that when we think about these things on the number line, we know that 4 and minus 4 are the same distance from 0. And we started talking about something called the absolute value of 4. The absolute value we show with these lines. And the point of this is that whenever you talk about, for example, distance, you can't talk about negative distance. So the absolute value helps to take care of that. And so we learned that the opposite of 4 is minus 4. And we also learned that if you add two positive numbers, you get a positive number. If you add two negative numbers, you get a negative number. Right? That's what this is saying in this paragraph. But how do you show that? If you go to the number line, sorry, it's not straight. I'm doing this with the mouse pad. But if I add two positive numbers, say 2 and 4, really to do that, I'm going 2 on the right, and then I'm taking that 2 and I'm adding 4 to it. So both of these are in the right direction. The result, which is 6, will also be positive. If I was to do the same thing in the opposite direction, minus 2 plus minus 4, you would get minus 6 in the same way. Because I went minus 2 to the right, and then I went minus 4 to the right. When I add those two lines, if I was to pick this little line up and put it in, it would be at minus 6. So you start to say to yourself, what's the difference between addition and subtraction? Well, that's a valid question. When subtraction was first introduced to you, you had the notion of counting a set of things, 10 balls, and you subtract out 2 balls, you're left with 8 balls. Those are physical things you thought about subtraction as taking away. But when you start thinking about subtraction on the number line, and we introduce the notion of signs, positive and negative, you think about it in a slightly different way. So you see here that if they take, for example, minus 4 plus 3, you get minus 1. Well, why is that? This seems counterintuitive. But let's look at that. Zero. Everything to the left is negative. Minus 4. That is a minus sign. And just make sure we got it. And we had plus 3. So what happens if I add minus 4 plus 3? Now, the notion we're thinking about is moving along the number line. If you want to still think about subtraction in the way that you have in the past, What does negative 4 balls mean? It's a little abstract in thought. But if I think about this in the number line, if I start at -4, if I go -4, and then I turn around and go +3, where will I end up? -1. On the number line, if I go -4 and then I go +3, I'll end up at -1. I can even think about this as balls. If I had a box and the box didn't have 4 balls, because if you think about -4 as not having, then you could say this box is deficient by -4 balls. And if someone comes along and gives me 3 balls, this box is now only deficient by 1 ball. And so it's still a -1. It's a little bit more abstract to think of this as you did in the past, like subtracting things out. That's why I'm proposing that you think about it in terms of the number line. And what we're actually doing is introducing this whole idea of numbers having signs, positive signs, negative signs. When we start to do problems, like problem number 4 at the bottom of the page, and you start thinking about a hiker that's walking 3 feet below sea level. If this is sea level, and we talk about 3 feet below sea level, she increases her elevation by 5 feet. How would you express this in positive and negative numbers? So now we're definitely on the number line, because who can tell me what sea level represents? Correct, it represents 0. It's the transition between positive and negative. And if you're 3 feet below sea level, you're at -3 feet. And if you're told that you move 5 feet, increase by 5 feet, that's a plus. So now in the language, I'm telling you, below sea level, you got to pick up that that's -3. Increasing by 5 feet, you got to pick up that that's +5. And now you know what this result is, of course, is 2. But the key thing that 2.1 is trying to do is introduce you to the notion that there are positive and negative numbers, that those things actually, through that problem we just did, we can relate those to the real world. And we're going to start doing problems where things can be positive and negative. It's 3 degrees below 0. It's 100 degrees above 0. Numbers now have the notion of positive and negative. It's not just taking away, but it's how things change. The temperature changes. How does it change? So we talk about that in terms of positive and negative numbers. Moving on to lesson 2.2. When you have positive and negative numbers, there's a notion of being able to do operations with them. And here they're showing the operations of multiplication and of division, product and or quotient, 2 other terms for multiplication and division. And the key thing you have to note here is I showed you on the number line adding and subtraction and how the signs were changing. Well, when you do multiplication, there's a set of rules. You know, a positive number times a positive number is positive. A negative number times a negative number is positive. And a positive times a negative or a negative times a positive is negative. Well, you say, why is that? It's beyond the scope of this lesson to tell you that. Today, just remember that if you have a positive and a positive number multiplied or divided, you get a positive. If you have a positive and a negative, you will get a negative. If the sign is the same, you get a positive. And that's summarized to the right. There are several problems provided at the end of this page to help you really understand that. And basically, you're doing the multiplication and then you're checking against this rule. Negative times negative is positive, positive times positive is positive, etc. So we'll just pick one problem to look at here, and I think it's really just doing those problems. So if I were to give you something like 12 times minus 1, what do you expect that to be given the rule? Correct. Minus 12. If I gave you minus 3 times minus 3, what do you expect that to be? 9. If I said 9 divided by minus 3, what should that be? Correct. Minus 3. So this is an example of using that rule. Again, do the problem set, you should get it. It's basically knowing the rule. Positive times positive is positive. Negative times negative is positive. Negative times positive or positive times negative is negative. All right. So we're just reviewing. The distributive property is all around how things are grouped. I say to you that you can use the distributive property to simplify an algebraic expression. The example given here is 2 times the parenthesis 4x minus 5 parenthesis minus 3 parenthesis 6x plus 5 close parenthesis. And so if you were trying to simplify this, they show that you can actually multiply this 2 through. This sounds familiar because you saw this before. And you can get, if you do each term, you can simplify it. Now, in most cases, you're going to want to solve this for x. That's coming. So when you have like a very complicated thing as what's presented here, you use the distributive property to actually manipulate it to get it in a form that you can solve it. So some things came up. I showed you the number line earlier, but I propose that if you have two numbers, there's a set of rules. It's not in the book. This is something that I actually articulated. If you have a negative plus a negative, the result will be negative. You're going left on the number line, you go left again, both go in the same direction, the result will be negative. If you have a positive number and you add a positive number, you're going to the right on the number line and you're going to the right again, you will get a positive number. If you have a negative number and a positive number, you do the subtraction, the actual operation between them, and the result will always have the sign of the bigger number. Now, let's look at that. So we have our trusty number line. What we talked about is that if you add two numbers that are positive, those arrows both point in the same direction. The result will be positive. Because to get this, you put these two together, they're both positive. There's no way that number could be negative. The same happens if you have two numbers that are negative and you add them. The result will be negative. But what happens if I have a positive and a negative number? So if I have a big positive number, a bigger positive number, and a smaller negative number, can you guess what the result would be? Positive. One example could be 5, which is the bigger positive number. So plus is understood, so I won't write it, minus 3. The result is 2. What actually happened is you took the sign of the larger number. What if we do this with negative? And this is 0. I wish I had a pencil and make it so much easier. What if I had a very large negative number and a smaller positive number? So what if my negative number was 10? This point is 10. And my positive number is 5. Well, you can see, even if I was to roll back this negative number by the amount that's positive, you would still have a negative result. So the rule holds true. If you have a negative and a positive number and you're adding them, take the sign of the bigger number. I've shown it to you intuitively here. Again, this is not your book. That's something that I wanted to share. Going on to 2.4. What we're showing now is really all about this term equality. When I say something is equal, 4 plus 17 equals 21. If I change something to the left-hand side, I must also do it to the right-hand side of the equal sign. Here, I can change this by adding 5. But if I do that and I don't do it to the right-hand side, this thing will not be balanced. The left-hand side will be bigger than the right-hand side. So to maintain equality, what I do to one side, I do to the other, which is demonstrated here in this first line. This holds true for subtraction as well. And this will come up over and over again when you start solving algebraic expressions, where algebraic expressions have variables, numbers, and operators. We learned that in chapter 1. Here, an expression is given, a plus 3 equal 14. What's on the side with a? 3. If I wanted to know the value of a, I have to get it on one side of the equation, on one side of the equal sign. So I already learned above that if I subtract 3 from one side and subtract it from the other side, this equation is balanced, meaning that it's true. This equality is still true. If I only did it to one side, it would not be true. I can get an answer for A. This is also shown for B on the right-hand side. So let's look at one of the problems that is given in the text. All right, we have 8 plus M equal 13. First of all, this is an algebraic expression. Numbers, variables, operators. We have them all. This is an algebraic expression. The variable is M. M is unknown. In this simple problem, you can probably look at this and guess the value of M. But don't do that. Instead, look at what's here with M. Plus 8. There's a plus on this side, right? It's understood. M is positive, 8 is positive. So if I wanted to get rid of 8, I could minus 8 from both sides. So all I'm doing is rewriting. Come on. Sorry, guys. This is really hard to write. It takes a lot of dexterity. So I added minus 8 here. and minus 8 here. So this equation is still balanced. If I do this, minus 8 plus 8 is what? 0. So that term drops out. So I'm left with m is equal to 13 minus 8, which is, don't write 5 to the right, write another line like this. One thing we're going to be doing going forward is really trying to write step by step from left to right so anyone coming behind you can understand what you did. All right. I think that's pretty straightforward. So we're going to move on to the very last part of this chapter. Oh, did I skip one? Yes, I skipped one. Sorry. So equality is still the main topic here. And just like when you added and subtracted a number from both sides, if you multiply one side by something, you must multiply by the other. Here, we multiply one side by 5, so we multiply the other. It kept the equality true. And if you divide, the next line is if you divide one side, we divide it by 3. It held that this equality is true. If we did this to one side, it would not be equal. If we did not do this to both sides, we would lose the equality. What you do to one side, you do to the other side. Now below, they're actually showing this with an algebraic expression. So we will multiply them by 3. We can just divide by 3 on both sides. Well, why did we pick 3? We're trying to solve for n. And so to get n by itself, I can see that n is divided by 3. And we did talk about last time that in algebra, we rarely write n. Come on. Let me see if I get it fatter. We rarely write n divided by 3. That's very rare. We write n over 3 to show division. We rarely write n times 2. We write 2n instead. So that's the notation we're using. All right. So if we had 3n equal to 15, what could we do to the left-hand side to get n by itself? Well, we can see that if we divide by 3 on the left-hand side, n would be by itself because 3 divided by 3 is 1, and we'd have n. But to hold the equality true, we'd have to do it on the right-hand side as well. And this would result with n equal 5. So there are several problems on this page that exercise this notion. The question you always say to yourself is, what do I have to do to get the variable on one side of the equal sign? And in doing that, you actually solve for the variable. This is what you're always asking yourself. All right. Now, we did two things. We did problems where to get the variable isolated by itself, we had to either add a number or subtract a number. But now we've taken it a step further. There's two things you have to do now to get the variable by itself. And looking at this first one, 2n minus 7 equals 19. We can see first of all, we can see that on the left-hand side, we have the variable n. Our objective is to solve for n. We want to get n by itself. We can see that there's a plus 7 and there's a 2 multiplying. So the first step would be, the easiest step would be to add 7 to this side. And I know if I do it to this side, I must also do it to the right side. So if I do that, this term goes to, correct, to 0. So we copy down the terms. 19 plus 7, correct, 26. So now, that was the first step. That was step 1. Now, step 2 would be to divide. If you do this, 2 over 2 goes to 1, and n, since I'm running out of space right to the right-hand side, is equal to what? 13. We did 2 steps. There was a 7 minus 7, so we added a 7. There was a 2, so we divided a 2. But because we did this to both sides of the equation, the equality was not changed, and we were able to solve for the variable. I can tell you that coming up later in the book, there's going to be lots of problems. They're going to get very complicated, a little bit more complicated, where these terms that are multiplying could be negative, could be positive. So we'll be using the negative positive rules and things that we've learned today. So I hope this is helpful. This is a new format, trying out something new. Thank you so much. Remember, math is definitely fun. Bye, y'all.